Let's go ahead and get this started. Thank you everybody for coming out today. It's been a wonderful couple days with this conference, and we're getting closer to wrapping it up this afternoon. So definitely appreciate your sticking through us this afternoon. Sometimes the afternoon of the last day can be a little bit rough, but hopefully this will be well worth it, both for this and a couple of the other presentations that look like they're pretty awesome and following this. So today we are going to be discussing machine learning, specifically using AutoML and how it can help make the whole machine learning process a lot easier for you. My name is Shane Milton. I am a technical architect with Clean Slate. We are a consulting company here based out of Carmel. We have a focus on the cloud, everything from migrations to assessments, development and design. Pretty much anything in the cloud is something that we do. I personally have been in the Azure space since I believe it was October of 2008 when it was announced. The day Azure was publicly announced was also the day I developed and deployed my very first Azure system, and I've really been dabbling and playing in Azure ever since. The past 2.5 years or so, I've had more of an emphasis in machine learning, both in the cloud and on-prem, and I've had some systems in production with machine learning for the past couple years and have had a lot of success. I'm by no means an expert with machine learning. I consider myself more a dev who found a really cool tool, and I've had a lot of great success with it. So I'm happy to share what I've learned with you, and I hope it can help you. So what is machine learning? What is auto machine learning? What is AutoML? This term AutoML is a term that's really overloaded in some ways, and we're going to really get into defining this and where it plays in the machine learning realm. We're next going to jump into some code demos, and we're going to be using ML.NET, which is one AutoML framework. And then after we're done with that demo, we're going to step back and talk about a couple other frameworks. Teapot and Scikit-learn are a couple Python frameworks that we're going to talk about, and we're actually going to look at how it solves things in different ways with different biases and perspectives. So AutoML itself, the term, it's a type of framework. Just like an ORM is a type of framework, AutoML is a type of framework. Now, everybody seems to like to put AutoML in the name of their brand, but don't let that confuse you. No one company has a trademark on the term AutoML, and everybody AutoMLs and everybody AutoMLs differently. It's just a type of framework. And one example of that is Google AutoML. It's simply called Google AutoML. And well, it's just their flavor of AutoML. Now, lastly, don't confuse an AutoML framework with a machine learning framework. They are two totally different things. A machine learning framework is a framework that does all the training of these models and processing of the data. An AutoML framework is more of an orchestration framework that leverages those machine learning frameworks. Sometimes they get bundled into one big mega framework, but these are really two different types of frameworks. So before we get too deep into AutoML, let's talk about machine learning itself a little bit. If you have worked on a machine learning project, this should look incredibly familiar to you. For the SDLC of that project, there are kind of 3 difficult steps. I'm only showing you 2 of the 3 difficult steps. The first difficult step is really coming up with an idea of what you want to do with AutoML or with machine learning. Before you know what you're going to do with this machine learning, there's no sense in starting. So having an idea of what you want to do is the first hard step. And part of that step is actually just asking the right question. You may have an idea of the space you want to do machine learning stuff in, but you got to make sure that you have identified the actual questions you want to ask. Once you've done that, you can actually start the project, and that's where this SDLC comes in. The second hardest step is this prepare phase. This is where you need to prepare your data and get it ready for machine learning. Arguably, and I would even agree, that this is really the hardest step of machine learning projects, is getting your data, cleaning your data, making sure your data is solid, has no gaps in it. There's a lot that goes in here. Once you've prepared your data, and you generally need a combination of data analysts and engineers and possibly even data scientists as part of that process. Once you've cleaned it, you can start to then get into the actual machine learning portion of the project. This is where you would go and choose your machine learning algorithms and configure those machine learning algorithms, and then feed your data into those machine learning algorithms and generate some trained models. Traditionally, there is a lot of time spent in this phase. We'll get into what and why later, but the point being, for this design and train phase, there's a lot of time that goes into this, both for people and for systems. The last phase is really the easy one, deploy and consume. Well, when you have a trained model and you're ready to go use it, the deploy and consume is really by far and away the easiest part of the machine learning process. Personally, most of the trained models that I've built and consumed, I've actually deployed them behind REST services, so I can just have some quick gets and get REST APIs that will go generate some predictions and give me a quick answer, and that way I can reuse those anywhere and everywhere I want. There are other places where you might push these down to a mobile phone or an IoT device, have them in some other manner, whether it's on disk in a database, putting these trained models wherever you need them. That's really the easy part of this. Now, when AutoML steps in, this process looks very similar, but there are a few stages that change a little bit. The first stage, the data preparation, this does not change drastically, but what you'll find as you work on a few machine learning projects is that there are some common types of problems that have common types of solutions. Let's pretend we were working with weather data from a weather station. And let's say we had 20 years of data from that weather station. That's an awesome set of data to be able to train some models on. But real world happens, and sometimes that weather station goes down, whether it's a power failure or I'm performing maintenance on it. So there will be gaps in that data for 20 years, for that 20-year history. Now, one common way to solve the gaps in that data is to just generate averages based on the day before and day after. And that's where some AutoML tooling comes in to help you. It can solve some pretty common problems for you. It's not a silver bullet. It's not going to perform all of this data preparation for you, but it does sometimes offer you some additional tools to help make that a slightly easier process. But where AutoML really kicks in is this middle stage, the design and train. With a traditional machine learning project, you would have data scientists, you would have engineers spending a lot of time selecting and configuring these algorithms, testing them, training them, comparing them to previous runs, and all these not only take a lot of people time, but it also takes a lot of computer time. With AutoML, you can kind of remove most of the people time part of that process, and instead you're just spending a bit more computer time. And relatively speaking, CPU cycles are a heck of a lot cheaper than human billable hours, especially when you have data scientists and engineers on a team of multiple people working full-time or full-time-ish at this process. So AutoML largely replaces that human level of effort in this design and train phase of the SDLC. Now, the output of an AutoML framework is largely the same as the output of a machine learning framework. You have a trained model or something like a trained model that you can then go deploy and consume, and not a whole lot changes on that last deploy and consume step. So this has been an SDLC look at machine learning AutoML. Let's look at the architecture of this a little bit. Again, if you have been part of a machine learning project, this should look incredibly familiar to you. Almost all machine learning projects go through an architecture something like this. There are certainly derivations of this, but they will all build on top of this. They won't be too terribly different from this. And by the way, this is specifically for supervised training problems. There are some unsupervised and other type of problems where it may look a little bit different, but in the supervised space where you have data to train on with known answers for that data, this is definitely what that architecture is going to look like. So you start out with your training data and your test data. Well, the first phase of the SDLC has already prepared that for us. So we can take the output of that first phase and feed that into our training data and our test data area here. The next step in this architecture is we feed that training data into a machine learning algorithm. This is where we start that second phase of the SDLC. We start training algorithms, selecting algorithms, configuring algorithms, and we spend the CPU cycles to generate trained models. The output of that box going down to our hypothesis is a trained machine learning model. Once we have that trained model and we we put our test data into that trained model, we get some metrics for our performance. And at that point, we can then have a feedback loop that goes back up to our machine learning algorithm process to educate us on whether or not we need to change things and hopefully give us some kind of insight on what we need to change. Now, doing this one at a time is not very efficient. So those of us who have done this before, we realize we quickly want to do this multiple times in parallel. So we might have algorithm 1 on the left side and algorithm 2 on the right side. This is really the exact same architecture that we looked at on the previous slide. It's just 2 of them in parallel. So I could have algorithm 1 on the left side, algorithm 2 on the right side, train them both simultaneously, and when I get metrics for them both, I can compare those metrics, and I could discover that algorithm 1 is better than algorithm 2. Now, doing 2 at a time may not be the best. We might want to do this 10 at a time. Now, there's 2 things though that this feedback is providing us. One, it's giving us feedback on which algorithms are better or worse, and 2, which configurations of an algorithm are better or worse. I give the example, we might have algorithm 1 on the left side and algorithm 2 on the right side, but another scenario is we might have the same algorithm on both sides, just with 2 different configurations. So the feedback is not just on which algorithm, but is also on the configuration. Now, how do we decide which algorithm to use? So there are some tools that can help give us some rules of thumb on which algorithms might be a good algorithm to use. And this is just a cheat sheet from Microsoft for Azure ML as just an example. And there's some other cheat sheets that give you some idea here. And I'm not at all expecting anybody to process and absorb this. Just realize that there are actually a lot of algorithms that are used in a lot of different scenarios, and it is not entirely clear which one is good. Even if you have a cheat sheet like this, it's still not clear which one you should really use. It starts to narrow them down a little bit, but not a whole lot. So I'm going to move on just because this is kind of overwhelming, but there's a lot of I don't know and randomness that goes into picking these algorithms. And in fact, also the same thing with the configuration for the algorithms. And this is why this XKCD slide is actually so funny. There's so much truth in this slide when we're doing traditional machine learning development and even with AutoML to an extent. A lot of times we don't necessarily have an idea of what the best thing is to use. We just try something different and see how it looks. And one of the algorithms on that previous slide was a decision tree. And as technologists, we all generally know what a decision tree looks like. You got a tree with branches, and each branch is based on a decision. In this case, the question might be, is this number greater than or less than 100? So we can envision a decision tree. But when we configure that decision tree, we have variables such as the number of branches that are allowed to be in the decision tree. How deep can those branches go before it stops being allowed to branch anymore? And again, we can envision what those questions are asking, but there's no way we can intuitively know what the right answer is. Is it good for a decision tree to have 2 branches? That's probably definitely the wrong answer. But what about 20 or 200, 2,000, 2 trillion, what is the right answer? What you'll find for something like that is you would intuitively think the more branches you have, the better it is. But that's not really true. First of all, if you get too many branches, you can have your model be overfit to your data. But secondly, it's not even a question of diminishing returns. There are actually times where fewer branches actually give you more accurate results. So it's not something you can just intuitively figure out. Now, data scientists might have some rules that they go by where certain scenarios it does make sense to have fewer or more branches, but I don't have that knowledge. I'm a developer. I am not a data scientist. So for me, I just have to use random values for these configurations and finally just try so many different permutations until I find the thing that works best. And by the way, every one of those algorithms, let's hop back over here. Every single one of these algorithms has a different set of configuration variables. So how you would configure a decision tree would be very different than how you would configure a Bayesian linear regression, for example. So once you research and finally understand that one algorithm, well, that's 1 out of 30. Good luck doing that with all 30 without becoming an expert at this. It takes a lot of time to really be able to comprehend and understand all this. So back to the machine learning architecture here, that middle section is where all of this algorithm selection and configuration comes into play. With AutoML, we get to change that drastically. Instead of me picking an algorithm and configure it, instead, it's almost like we take this whole architecture and we shove the architecture inside of that middle box, and we kind of have an inception of machine learning architectures. So with traditional machine learning, I would go through this architecture to train a single model. Sure, I can parallelize it and have n of these models, but with AutoML, I don't have to. With AutoML, I get to use the AutoML framework to take care of that algorithm selection and configuration process itself inside of this one box, and I can instead treat this as a single iteration through the training process. I still feed my training data in, I still get a trained model out, and I still feed my test data into that trained model to get metrics. And maybe I still get feedback so I can reconfigure that middle box, but instead of reconfiguring it by selecting a different algorithm with a different algorithm configuration, I would instead change the configuration of the AutoML framework itself and how I'm consuming that. So what I have found, and like I said, I've had some of this in production for quite a while now, and what I have found is that there are a couple ways that this really helps you as an engineer. Firstly, I don't have to spend the time learning all the data science around these algorithms and how I should use them, how I should configure them. A lot of that gets abstracted away from me by this AutoML framework. I get to just learn how to use this framework that abstracts all that data science away from me for this development. Secondly, I've found that using the AutoML system, it actually produces results better than what I've been able to do myself. It's not been 10 times better, but it's been able to bump percentage points up a little bit. And that's after I have spent man weeks trying to get the best model, the best algorithm with the best configuration. So not only is it saving me a ton of time, it's actually giving me better results than what I was able to do myself with a traditional process. So is this too good to be true? And the answer is kind of yes and no. So yes, this is pretty darn good. Now, can a data scientist do better than this? Yeah, probably, maybe, eventually, with enough money and enough time. But the other question, are you a data scientist? I am not. If I wanted to become a data scientist, could I outperform an AutoML system? Possibly, but I'm not, and that's not something I'm wanting to do. But yet, I want to build machine learning systems. So there's this company called Kaggle. They've been around for a decade or more. I'm not sure when they were formed, but they actually started in Australia and they quickly moved to the Bay Area. A few years ago, Google acquired Kaggle. And what Kaggle has done is they have hosted, facilitated, and managed machine learning competitions. These competitions have ranged from free and educational to having rewards of $100,000 plus to the team who's won this. And the teams that participate in these competitions vary wildly, from single person teams to multiple person teams. The teams might be students, they might be mathematicians, they might be data scientists, they might be professional engineers, or a combination of all of these. And these competitions and Kaggle, they use Kaggle's platform in order to be able to create and submit machine learning systems that can then compete with one another against data that they've never seen, in order to see which system is able to perform the highest accurate predictions based on the unknown data. And what Google did last summer is they hosted one of these competitions, and it was a weekend-long competition. And the whole point of the competition was to compare all of these teams against a single day's worth of AutoML submissions. So they gave Google AutoML 1 day to come up with a solution. And then they had these teams compete for the entire weekend to try to provide a submission that beat AutoML. And what they found in the very final minutes on Sunday of that weekend, they had a single team make a submission that beat the AutoML generated system. So you had quite a few teams competing against, for the whole weekend, against the first day of AutoML, and you had one team in the final minutes beat it. All the other teams were coming up with predictions that were subpar to the AutoML system. Fast forward a month, they let these teams continue improving. Fast forward a month, and they finally saw that 10% of the submissions were able to beat the first day AutoML implementation. Fast forward 2 months, and it was around 20 to 25% of the submissions were able to beat the first day. But the point being here is that 1 day of AutoML work it really had staying power when you were comparing it to all these teams of data scientists, mathematicians, engineers working for weeks and months to do better. So this is where the is it too good to be true? Yes and no. Data scientists can do better maybe eventually with enough time and money, but this is pretty darn good stuff. So with that, we're going to hop into a demo, and I will say this cartoon's a little bit funnier in person when I have a hot dog sitting in front of me. But what we are going to look at is we're going to look at a data set called the MNIST data. It has approximately 70,000 images in it. Each image is an 8x8 pixel image representing a number 0 through 9. So on this slide, you see a few examples here. There are 70,000 of these things. And we're going to look at an AutoML system that's going to train some models over this data and try to essentially read handwritten numbers. So I'm hopping over here into VS Code, and we are going to be using a framework called ML.NET. It's an open source framework that Microsoft has created. I believe it leverages TensorFlow for the ML engine underneath. ML.NET is a bit of a combination framework. While it uses TensorFlow underneath, it's got its own machine learning wrapper around that. So this framework has both a machine learning framework as well as an AutoML framework. This is one of those mega frameworks where they're both bundled in together. And what we're looking here with this .NET Core code is a console application. And for those who are not familiar with .NET, that's okay. This is simple code to look at and understand. Now I'm going to scroll all the way down just to show you almost everything in this code base. It's pretty much a one file application, and there's 130 lines of code here. As you can see, we're writing a whole bunch of output to the console. I've got quite a few comments in here. I actually counted the functional lines of code, and I believe there are 20 functional lines of code in here. So for this console application, what we do is we are going to take the inputs from the command line that come in this array of strings. We're only expecting and accepting a single integer. So what we have is this time that we want to train our machine learning model on. So in this case, we'll default at 60 seconds, but if we pass in a different number, we'll override that 60 with a different number. So I'm going to hop down into my terminal down here. We're just going to really quick call .NET. Actually, I need to get my source. .NET run, and we're gonna run it for 120 seconds, 2 minutes. And while it's running, I'm going to shrink this back down here, and we're going to keep looking at this code. So first few lines of code here is just parsing that 120 out of the command line that we called. Next, we're going to instantiate this thing called an ML context. This is our entry point into the ML.NET framework. And we're going to use that ML context to load data from some CSVs. So let's take a look at one of these CSVs real quick. It looks something like this. Not very elegant here. I'm going to scroll over just a little bit. I'm at the top, and I'm going to hover over this last column here. And what you see here is that there are 65 columns in a CSV here by that tooltip. The first 64 columns, well, those are the pixels of the images. Remember, they are an 8x8 image, so 8 times 8 is 64. This has 65 columns in it, so that 65th column is the answer column. So the answer column real quick we'll look at. The first one is a 0, so that means all the pixels to the left of it represent a 0. The second one is a 1, so all the pixels to the left of it represent a 1, and 2, 3, 4, 5, so on. They're sequential at the beginning, but as you hop down into the data later, they're fairly random. So that last column is the answer column, and the other 64 numbers are the pixels. Well, what do those numbers mean? They are values from 0 to 16, which means there's 17 possible values there, which is a little bit odd. So rather than them being hexadecimal, they're septadecimal. But a 0 represents a white, and we're going to hop back over to the slide real quick. Looking at each one of these images, those 8x8 images, a 0 represents a white here, a 16 represents a black, and numbers in between is a grayscale value. So that's what these numbers in this CSV represent. Just to give you a little bit of a visualization, I took those first 2 columns of data and I put them in here. I kind of converted them to a septadecimal format, so 0 through 9 and then A through F. And on here, if I do find and replace, and I replace the 0 with a space, you'll find that very quickly visualizing this data, which is a pretty poor man's way to visualize it, you see that top one looks kind of like a 0 and the bottom one kind of looks like a 1. With grayscale values, that 1 looks a bit cleaner than what it is there. But in a nutshell, that's what these CSVs are that we're loading. So back to our code. We're loading these CSVs from text. Our ML context gives us a little helper function to do so. In our CSV, we're saying the first 64 columns, and that's 0 through 63 with a zero-based indexing. The first 64 columns are our pixel values, and the 65th column is our answer. That's the number that the pixels actually represent. Now, for those of you who are familiar with .NET, there are other helper functions here, and the one that I actually always use in my systems is this load from enumerable. And what this lets me do is it actually lets me load this data easily from a database, whether I've got something like Dapper or any framework, some kind of ORM, or any way of loading this data from a database. I can very easily provide enumerable objects into this to populate this data set pretty quickly and easily. So we load our trained data and our test data. And then this next line, this is the magic one-liner. So when we called this code from our terminal at the bottom, which we can see it wrapped up, when we called this down here, we called it and we told it that we want it to run for 120 seconds. So when our program ran, it spent 120 seconds on this one line. This is really the one-line magic sauce. So what is this? We're taking our context we generated above, we're calling the .NET, or I'm sorry, we're calling the auto function, which gets us into the AutoML portion of the framework. And then we tell it we're going to create a multi-class classification experiment that's going to run for a certain period of time. And we want it to execute over our training data. And by the way, here's the column that represents our answer within that training data. So let me repeat that. We are taking our ML context object and we're getting into the ML portion of it. We are creating our multi-class classification experiment to run over our training data. Now, because we're trying to read these numbers, these images, let me hop back over to the images just to help us visualize this. Because we're trying to read these images, we know that there are 10 different numbers that each image can possibly be. So that means we have a multi-class classification problem here. How many classes do we have? We have 10 classes, 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So once we've generated this multi-class experiment and trained it over this training data, the result is this thing called an experiment result. From this experiment result, we can say, hey, give us our best run. Now remember, when we're training with an AutoML system, it's actually going to figure out what the best algorithm is and the best configuration. And the way it does that is it really trains a whole bunch of algorithms with a whole bunch of configurations. In the traditional way, when we've done that, we've kind of used randomness to hopefully stumble upon the best configuration. AutoML frameworks, they also use randomness to help them find those, but they can use statistical models and they also have some level of intelligence in order to eliminate bad configurations for the type of problem they're working with and bad algorithms for the type of problem they're working with. The more time you give them to run, the better they get, but you can also time box them, which is incredibly helpful when you're iterating through the development process. In this case, it's also helpful for demonstrating because I was able to let this run for 120 seconds as opposed to 12 hours. So with the experiment, we were able to get the best run. If we really wanted to, we could go in and grab run details, which is a collection of all of the runs, but we're just going to go with our best run here. We're going to call it our hero model. It's now a trained model. And from there, we can take our test data and make predictions against our test data in order to get some metrics from those. And at that point, if we hop back to our architecture here, we have now trained a bunch of models. We took the best one. We took our test data, sent it to our best trained model in order to get some metrics out of it. So this is really the end of our architecture if we don't have anything to improve upon. Now, in the SDLC, once we're done with the design and train phase, it's time to actually deploy and use that. So we even have code in this application to do a mock deployment and consumption. So we've got a few lines of code here where we're going to take our hero model here and we're going to serialize it to a byte array. The framework gives us these helper functions, make this incredibly easy. And this byte array is something that's actually manageable to work with in all the times that I've used the system to generate trained models on. So where I have used this has been in the energy industry, and we have trained some of these models with hundreds of megs of data. And the output at this point is oftentimes a 450K file once I take this binary data and save it to disk or save it to a database. So being able to take a 450K trained model where I can deploy that to mobile phones, IoT devices, or web servers for final use is something that's incredibly manageable, even though I've trained it on hundreds of megs of data. So in this case, we've serialized it to a byte array. I'm going to skip over some of this code. We'll look at the outputs of writing all this to console in a moment. But down here, we are going to create a brand new ML context, just so we're not reusing the one we had before. So this brand new ML context has no context, no idea of what we've already done in this program. We're going to use this to deserialize our trained model binary into this thing called a prediction model, it's a transformer. We're going to take that prediction model and generate a prediction engine out of it. And with that prediction engine, we're going to loop over some data and make predictions. So this is kind of our mock consumption once we've mock deployed this model. Now, what is it making predictions over? Well, if I had more time, I would be showing you a demo where I've got a stylist handwriting some numbers and we would do some live translation. Instead, I've just got a couple hard-coded values where I've got an array with 64 values. In this case, this top array represents a 7, this bottom array represents a 1. And if we hop to the end, we see that there are no answers in this array. So what we're feeding into this prediction engine is just data that represents a number, a 7 and a 1. And we're going to loop over this array here, and we're going to make the predictions and output the results. And that's the end. So what this code did, everything we just looked at, we imported our test data from CSV. We imported our training data from CSV. We had our one-liner up there that it spent 120 seconds training models and over that training data. It chose what the best model was. And I know people who are familiar with machine learning have the question, what does best mean? In this case, we're using defaults, but when I instantiate the context up there, I can actually pass in some configurations to define what metrics I want it to use to determine best. In this case, we're just using default because that makes nice, cleaner demo code. But it will take the best model out of all the models it trains, and then we were able to take that trained model, produce predictions based on some test data, get metrics, serialize that model into binary that we could have sent over the internet easily to a mobile phone, and then on that mobile phone we could have done predictions like we just did right here. So when we called this, we had it run for 120 seconds. So let's look at the output here. We see when we called it .NET Run for 120 seconds, we see that it was able to train 9 models in that time. The more time you give it, the more models it can train. In this case, it was able to use the light GBM multi-trainer. What does that mean? Well, let's go to docs. We have a light GBM trainer model. We can go and see some details on this. And as we scroll down, there's a whole lot of information on this model, how it's applied, what it means. I don't personally know anything about this algorithm. I don't know anything about how to configure it. And that's the beauty of AutoML. I don't have to. Generally speaking, I don't really even care what this algorithm is. I just care that I have confidence in the process, that I let this system run for long enough to be able to not necessarily fully exhaust, but to, with a good enough level of confidence, exhaust enough of the possibilities in order to get me a trained model. And we even generate metrics to actually see that. So let's actually look at those metrics. So the metrics of the hero model with the training data, we're going to mostly look at these accuracies. Based on the training data, we believe we have a model that is 98.3% accurate at reading these 70,000 images. That means there's less than a 2% margin of error there. That's probably better than what I'm going to do personally as a human. But remember, this is just metrics based on the training data. We haven't put our test data in there yet. So let's look at our metrics for the test data here, and we find it's not 98% accurate, it's more like 96.5% accurate once we actually put our test data in there. That's still pretty darn good for something that's only trained for 2 minutes. As we scroll down here, the other thing that we're outputting here are the predictions on the 2 hard-coded values that we looked at, that we fed the predictions into after we serialized and deserialized. And we see that it got the first number right as a 7, and it got the second number correct as a 1. Now, I actually ran the same thing earlier for 20 minutes. I did a .NET run 120, so that let it run for 20 minutes. In this case, it came out with an algorithm of fast tree OVA. So let's hop over here and see what that is. So fast tree OVA. There's actually a couple of things to look at for this. So one thing, let's talk about this OVA for a moment. That's the one versus all trainer. So we are doing a multi-class classification experiment. What that generally means is you want to have an algorithm that can classify things into n different classes. We have 10 classes, 0 through 9. But one versus all says we're not going to use a multi-class classifier. We're just going to use a 2-class classifier. And we're going to have one of those classifiers for every single class. What that means is for every image that we look at, instead of it going to a multi-class classifier, it will go to 10 different 2-class classifiers. The first of those 10 would be asking the question, is this a 0, yes or no? Yes and no are your 2 classes. And if it's a 0, yes, it would answer yes. If it's not, it would answer no. So this is a way where the AutoML framework actually tries to expand your possible options in a way that you might not originally consider. And there are sometimes some benefits to using 2-class classifiers over a multi-class classifier in this way. I just want to point out that there's kind of a couple other variables that might come into play, and I just want to make you aware of that if you stumble upon this. Now, what we really want to look at down here are the metrics. So for training for 20 minutes, over just our training data, previously with our 2-minute run, we had 98%. This is saying 98.5%, but that's our training metrics. That doesn't matter a whole lot. We care more about our evaluation, our test data. In this case, we saw 96.8%. Our prior one, we saw 96.5%. So yes, the 20 minutes training got us better, but it's not a ton better. The 2 minutes was surprisingly good. Now, what you'll find is you can actually get this number reaching 98% or so if you give it enough time. It'll take hours to do. But even our 2-minute run, it ain't bad. Now, hopping back over to our slides, what we looked at was the ML.NET framework. And there are some other options out there. A couple of things I want to point out are not all of these AutoML frameworks take the same approaches. Teapot, for example, it's an ML.NET, or I'm sorry, it's an AutoML framework, but its plan is not to give you the best of a bunch of models that it trains. Instead, what it tries to do is it tries to identify the best algorithm and the best configuration for that algorithm for you. It largely means the same thing when you think of it at first, but as you dig down into it, the benefit to doing this is that once you've identified it the very first time, you never have to go through this process again until you're really wanting to. Instead, as you have more training data to train over as time moves on, you can just train your one algorithm with this one configuration, and it saves you a lot of training time in the future as you continue to evolve and iterate. Now, AutoScikit-learn, this other Python framework, it has yet a different perspective. With ML.NET, what we looked at, the end result was a single model that we generated and consumed. With AutoScikit-learn, instead, it uses the concept of ensemble learning. And what that means is you don't get a single model necessarily at the end. You might have 3 trained models, and they might have different weights when they vote on what they believe and think the best answer is. So you might have one model that is really good for a lot of the data, but there might be parts of the data where it doesn't perform so well at, and it might be able to then grab a different model that performed better in that area, and it can use this group intelligence of multiple models to actually increase the performance and accuracy of your predictions. So not all ML frameworks take the same approach, but they all have some interesting and really valuable benefit that they can bring to you with your machine learning project. Another thing to point out is with Teapot, you don't necessarily get to tell it, I want you to run for 2 minutes. It has the concept of generations, where each generation can take different paths and different approaches in order to evolve your machine learning process. Whereas AutoScikit-learn and ML.NET, you can say, hey, run for 2 minutes, run for 2 hours, run for 2 days. So they're just different ways to get to the same end thing at the end, where I'm a developer who wants to do this machine learning project. I don't necessarily want to tackle all the data science here, but I really want to have some really good results in the end. And these other frameworks are some great options. There have been some other talks in the past couple of days that have touched on a lot of different frameworks here. So I definitely encourage you to take a look at these others. These are not necessarily the best ones. These are just the ones that I've got experience with, and I can definitely recommend using. With that, I'd like to thank everybody for joining. Now, I know there are some people in this talk who are new to machine learning, and I want to point out that that's okay. Everything we just talked about should be a great takeaway for you. But before you're ready to jump into this AutoML code, I'd highly encourage you to look at some of this introductory stuff here to kind of help you get caught up. There's a few easy courses to follow along that can really bring you a long ways. Next, the code that we just looked at is available in GitHub. These are some short links that will take you there. And by the way, there are also some code examples for Teapot and AutoScikit-learn. They've got some Jupyter notebooks to help you get through that code, and definitely encourage you to take a look there. And then if you really want to keep pushing yourself further, go to check out Kaggle. They've got some great competition there. Not only do they have some educational material for you to kind of learn on your own, but there's some community involvement that will also help encourage you and push you and challenge you to further your skills. And then lastly, as a thank you for watching, Clean Slate is offering a couple free consulting packages to anybody who'd like to join. If you're interested, hop over into our Slack channel, which is sponsor-Clean Slate, and ask about it there. We'll get you some more details. Thank you very much, everybody.
Yeah, thank you, Shane. That was very good. Actually, there was one question about one versus all would create an unbalanced binary classification, question mark?
Yes, it's definitely possible that it could be unbalanced. So you would generally want to figure out what would have the highest confidence level in each class, and that's what you would go with.
Awesome. Well, we're all, actually, there's another question in the room here. We got 1 minute left. Do the different models tend to fail on the same test images? If so, that would be useful for an error term. If not, then voting would be useful to improve results.
Yes, different models fail in the same images. I absolutely agree with the statements afterwards, but I also want to throw out, and I'm going to jump back some slides real quick. These images here show some of the complexities in reading this data. And for example, look at this 4 here. I guarantee there are a lot of models that are going to call that a 9. And you know what? Can you honestly tell me that you can definitively prove that that's a 4 and not a 9 in any certain way? So there are definitely images that are more or less impossible to tell what it really represents. So while your other statement is true, there will still be some of this problem data where you're not going to get perfect accuracy, or you can't, just because the data, the image is so poorly drawn, there is just going to be error there. And with any machine learning system, you have to plan for and have controls around when there's error that happens.